Thank you very much. Thank you very much for coming. My name is Adam Warski. I come from Warsaw, Poland. It would be great to be in the Bay Area right now, of course, but we all know what the circumstances are. So let's keep our fingers crossed for next year. And meanwhile, what I would like to talk about today is Project Loom, and how it fits into and how it might impact the landscape of concurrent asynchronous programming as we did today using futures and IOs and other constructs like this. So this will be some speculation, some overview of how things might look like. So first, it's always good to state what the actual problem is that we are trying to solve. The problem here is that we want to concurrently run multiple processes. And when we say concurrent multiple process, it's good to have some concrete examples in mind when thinking about the possible solutions. So this might be this might mean processing multiple HTTP requests in parallel. This might mean processing messages from a queue, integrating with some external services, or orchestrating workflows which integrate with these external services. This might mean processing background jobs, and there's also many other examples, but I guess you could pick your favorite one as we go through Project Loom and futures and IOs. So it's not only that we want to create and run concurrently running processes, but we want to create a large number of them, and we want to do it in a cheap way. And so why is that? Why a large number, and why cheaply? Well, first of all, it might be necessary. So it might be the case that the business requirements that we are faced with impose these requirements, right? So it might mean that we need to process a very large number of incoming HTTP requests, a very large number of messages from a message queue. But it might also be the case that it's easier to model solutions to certain problems by working with fine-grained tasks which are split into small chunks. So also from a programming model point of view, it might be easier to actually work with small processes which might potentially run concurrently with each other. So because of these two perspectives, we are very often faced with a problem when we need to run a large number of processes, and well, and they should be created, of course, in a cheap way so that our system is still performing well. So we are on the JVM, so that's our main constraint. We are assuming that we are on the JVM, and we have to live with the constraint that the JVM brings. The basic unit of concurrency in Java and on the JVM is a thread. A thread maps one-to-one to a kernel thread. So for each Java thread, there's a kernel thread. And these threads, well, they work well, of course, and we all better or worse know their characteristics, but they are not the best abstraction for our processes. They're expensive to create, they are expensive to switch. So switching our processing from one thread to another takes a long time. And we can only create a limited number of them. We are limited by the stack memory. So that's why we are looking for a better abstraction to actually solve our concurrency problem than the current Java thread. So before we continue, just a very short introduction of who I actually am and why I might be a good person to talk about concurrency and Loom. As mentioned, I'm the co-founder and CTO at SoftwareMill. We are a software consultancy and a development company based in Poland. We've been remote and distributed for 10 years, so remote work is nothing new to us. However, we would also like, of course, the lockdown to end. It's remote work nowadays, is nothing like remote work when you can actually freely go outside and meet people. So I've been developing mostly backend applications, starting with J2E through Spring, various Java frameworks, Scala frameworks nowadays. And I also do quite a lot of open source as like HTTP client, QuickLens. I also had an adventure with Hibernate when I was younger. So yeah, that's my background. So now going back to threading and concurrency. So what are the current solutions to the threading problem? Well, one of them is to create thread pools. This means that we create a pool of threads upfront. So we pay the creation cost upfront. So that's how we solve one of the problems, but we are still stuck with the other problems. We are still dealing with threads directly, we can still create only a limited number of these threads. They are still expensive to switch, and well, we have to deal with threads, meaning that we have to program against them directly, which is error prone and quite low level. And it's not an easy task to actually create a correct concurrent program using threads directly and synchronizing them using locks, semaphores, queues, and so on. So thread pools solve some of the problems, but still we are looking for something better. And that's how people came up with the abstraction of a future, or a completable future, as it's known in Java. A future is essentially a value, which is important. That's a value that you can store in a variable or in a constant. And it represents a computation that is already running in the background. And that computation will eventually yield a value of type T or end with an error. And these futures have very nice properties. So they are very cheap to create. You can create an unlimited number of futures. You are limited only by the heap memory, and they are cheap to switch. So the trick here is that there's an executor which actually has a thread pool in the background, and it schedules, it can schedule a large number of futures to run on a small number of threads. So this executor actually manages which future gets executed on which thread, and when one future is done, another one can be scheduled to run there. So we've got this thread pool, we've enriched it with an executor and the future abstraction, which is a value, and we are in a much better situation right now. Futures are also nice because we can compose them in two basic ways. So the first way is parallel composition. So we can create two futures up front. These two futures, F1 and F2, the computations they represent will be running in the background the moment they are created. And then we can compose the results. So once both are ready, we will get the final result. So this is parallel composition, and we also have sequential composition, where we first create one future, and once this future is complete, we create another future basing on the results of the first one. So that's sequential composition. We can sequence two computations one after another. And our programming libraries and frameworks have evolved in a way that most of the time, many of the modern frameworks now represent any potentially thread blocking or I/O operations using futures. So in a way, life used to be simple. So here we have a very simple example of a boring business logic code activating a user, which is finding a user in the database, which might be blocking, of course. It might involve I/O operations, and then conditionally activating the user in the database as well, right? So if we transform that to futures, well, the code doesn't look that nice, right? We now, because database interaction is a potentially blocking operation, it's now based on futures. So we have to use here sequential composition to compose the activate and find futures conditionally, right? Futures are also viral because now our activate user method needs to return a future as well. So our code isn't as nice as it used to be. So these are the three problems with futures that we will try to solve. The first one is lost control flow. So the code isn't as readable. So the business logic isn't as clearly visible as it used to be. Also, there's the problem of lost context. If we go back here, if there's an exception happening over here in database.activateUser, the stack trace won't be that useful. It won't include the fact that these methods were called before. Because the future will be scheduled to run independently of these other futures that have happened before. And also it's viral. So once one method returns a future, all methods that use it should return a future as well. And that's where Project Loom comes in. If we go to the website, we can see the mission of the project is to drastically reduce the effort of writing, maintaining, and observing high throughput concurrent applications that make the best use of available hardware. So that's the mission. What does it mean in practice? So Project Loom brings two major contributions. The first one is changing the basic unit of concurrency in Java. So this used to be a thread. Now it's still a thread, but it's a virtual thread. So virtual threads are just like threads, but they are very cheap to create and block. So we still have the same interface, the same base type here, thread. However, we create it in a different way. We create it using the start virtual thread method. And this is going to create a lightweight thread that doesn't map directly to a kernel thread. We can create loads of these in a cheap way and in a very fast way, just like with futures. And that's not a new concept. It's known in other languages as fibers, coroutines, processes, green threads, and so on, with some important details, of course, that might differ between these implementations. Here, what's important is that this concept will be present at the JVM level. So all of the Java language, all of the JVM languages will be able to benefit from virtual threads. So that's the first major contribution. The second is retrofitting the existing JDK so that it works well with virtual threads. So it means that any methods that used to block kernel threads will now become non-blocking. So they will still block, but they will block virtual threads, not kernel threads. So this means that if we have an input stream and if we read from the input stream, this will be now a non-blocking asynchronous operation. If we have a writer, a semaphore, or even a thread sleep, this will only block virtual threads. And behind the scenes, virtual threads work very similarly to futures as we have seen before. So there's a thread pool and there's a scheduler which actually assigns which virtual thread will run on which kernel threads. However, because this abstraction is now lifted to the JVM level, we don't have to implement it as a library on the using futures, for example, but it is present directly in the JVM, right? And a single virtual thread can run on multiple kernel threads. So here are some yield points. So where the virtual thread does some blocking operations. So then the scheduler actually will schedule other virtual threads to run in its place. So Loom also contains continuations, which are a lower level concept, and it's planned to include tail call elimination at some point, but that at a later stage. However, the main focus is on the virtual threads and on the retrofitting aspect. So Project Loom started in 2017, so that's 3 years ago now, as an exploratory or research project, and there have been a couple of iterations into the approach of how this should be done. Currently, there are early access builds available with Loom implemented, so we can actually see how Java works with Loom. But I'm not aware of any specific dates or any specific JDK versions where Loom will be included. So that's something to look out for. So we've seen the problems with the sequential code and what was wrong when we introduced futures to this sequential code. So now we can actually go back to the old days, go back to the old code, and we can once again write sequential code using blocking operations. So we don't have to be worried that we are blocking kernel threads because we are not. The database.find user, it might potentially block the virtual thread, but it will still be performant because there's the scheduler behind the scenes, which will actually make sure that the kernel threads, the resources are used to their maximum. But well, is it too good to be true? And in a way it is. A virtual thread is still a thread, meaning that the problems that we had with threads before, such as communication between threads, orchestration, so when threads should start and stop, how should the interruption of threads be managed? these threads, these problems still apply to virtual threads equally as they applied to threads as well. So we have some basic, a couple of basic ways in which we can combine multiple threads, right? So we can have computations which run in parallel and then are combined at the end into one final result. We can have arrays between two threads. So the first result is taken and the second is interrupted and discarded. We can have background jobs, and we can have many other types of concurrently running processes which are combined in various ways in our system. And we need a good way of managing that. And threads might not be the best answer over here. So we can try using semaphores, locks, queues, and channels to actually communicate and synchronize between threads to manage these various topologies of concurrently running processes. But then, well, we will probably sooner or later encounter deadlocks, race conditions, and, well, all the reasons why concurrent programming is considered to be so hard, and it is considered to be hard, as far as I know, at least. So while these primitives are great, and it's great that they are in Java, they are probably best used and best wrapped in libraries which hide them and allow us to use something better. So maybe, Loom was great for this sequential code, but what about concurrent programming? So maybe let's think, why did we use futures in the first place, right? So one obvious answer is for performance reasons. Asynchronous programming brings much better resource utilization of threads than when compared to the blocking style, and that is well studied and documented, so I won't repeat it here. But there's also the big gain of programming model, of capturing a computation as a value, which is equally important, especially in concurrent programming, which, as we've said, is quite hard. So anything that might make it actually easier, more readable, and more comprehensible is valuable as well. So the ability to capture computations as value here is very important. And, one way to reduce concurrency bugs is probably avoiding direct thread usage, and that's what we will try to do. So we will try to shift from using low-level concurrency primitives to some higher-level operations. And well, our goal in general is to use more declarative concurrency than imperatively using these low-level primitives. So futures gives, as we've seen, futures give us the basic building blocks, which are sequential and parallel composition. And using libraries, we can probably build some higher-level combinators on top of that. So as a very simple example of what's the difference that I'm talking about here, let's consider fetching data from two HTTP endpoints in parallel. And the first, let's use virtual threads and concurrency primitives, right? We are in the Loom world right now. So we have a virtual thread blocking method, which calls an HTTP GET. So if we need to run two of those in parallel, what we need, well, we need to have a memory cell where the results will be stored. We need to have a countdown ledge which will actually tell the main thread when the child threads, which actually do the parallel fetching, are done. Then we need to start the virtual threads, which will first invoke the HTTP GET, then it will fill in the memory cell, and it will count down on the ledge, right? So these are the child threads that happen in the background. And in the main thread, well, we have to wait until these child threads are done. And once they are done, we can get the results. So that's a lot of work, and it's probably quite error prone as well. So how can we do better? How would we do the same using futures? Well, if we are now back to the current world using futures, right? So our HTTP GET method now returns a future. Well, using futures is quite simple. We create one future, right? It's a computation which runs in the background. We create the second future, and then we compose the results of these two futures, and we are done. Much simpler, much less error prone, and much more declarative as well. So that's something that we definitely want to keep in our post-Loom concurrent world. So how can we take the best of both worlds? Well, it's shouldn't be a surprise that no style fits all use cases, right? So sometimes it's better to write synchronous sequential blocking code, right? But sometimes it's still better to operate on futures, even if we have these virtual threads at our disposal. So maybe we could speculate a bit how could a more friendly API look like here. So we are going back to the Loom world right now. So we have a virtual thread blocking HTTP GET method. And we can imagine that we have a run method which takes a chunk of code and actually executes it in a virtual thread, but still returns a future, right? So this is a library method that we would need, this run here. But then we can actually block on the futures in the main thread and wait until their results are ready. So this is already much better, right? Than what we've seen using the the concurrency primitives. Speculating even more, maybe we will have a library which has a run parallel method, which takes two chunks of code and a way to combine these results, right? So this method might be available in our hypothetical library as well. So Loom will still give us a lot of benefits when it comes to working with futures, but these futures are still needed somewhere in our concurrency libraries. These were the benefits of futures as we have seen. So let's reiterate maybe why would we use Loom, right? So Loom gives us a great tool to write non-blocking code in a blocking style and a synchronous style. And it provides a retrofit of the blocking APIs into non-blocking ones. However, it doesn't give us a complete replacement for concurrency libraries. It's useful to view a concurrent processes in a dual way, right? One way is to look at a concurrently running process as code, as a code written using the blocking style. But sometimes it's also beneficial to view it as a value which can be composed and orchestrated. So these are the two views, these two perspectives on a concurrently running process, which can be used interchangeably and should be used interchangeably to write concurrent programs. So let's speculate a bit more, like what kind of high-level operations might we expect on our futures in a Loom world, right? So some very easy ones are like retry, which retries a computation until it's successful. First, which is racing to computations. Delay, which delays the computation by a given amount of time. And if you try writing this down, it will turn out that all of these actually need lazily evaluated chunks of code, right? Retry needs to be provided with a chunk of code which can be evaluated multiple times. And that's represented by a callable interface in Java. And if we take a look at the executor service that is in Loom, it's extended comparing to the current one, you can see that quite a lot of methods actually do operate on callables. However, this executor service, while it's a good basic building block, it's in my opinion, far from perfect. So first of all, we've got a couple of process abstractions present in that executor service. So sometimes we have to work with callables, sometimes we end up working with futures, and sometimes we just get blocking methods which returns strict values, right? So invoke any corresponds to race, and invoke all corresponds to run in parallel, right? So why does this one return futures and why does this one return synchronous calls? Well, I understand the historical reasons, because we cannot break existing, we cannot change existing executor service, but we can probably do better in terms of these abstractions as well. There's also the with deadline operator over here, which creates a new executor service where all virtual threads have a deadline until which they have finished. Shouldn't this rather be a property of a process, not of the executor service? So there are some design choices here which had to be made probably because of Java conservative approach, but still in our concurrency library, maybe we can do better than that. And that's where we come to IOs, which can also play an important role here. IOs are frequently encountered in functional programming languages like Scala, Haskell, and others. And they differ slightly, but in a very important detail from futures. A future is a value representing a running computation, so it's an eagerly evaluated computation, while an IO is a value representing a description of a computation or a lazily evaluated computation. So this might sound like a small difference, but it makes a really huge difference when you get to use it. So these IOs is something like combining callable with a future, let's say. But IO offers much more than actually a callable, and there's a number of benefits that we might take. So first of all, with IOs, we have the opportunity to get really good cancellation semantics. So cancellation and interruption is a tricky subject to get right, and currently Loom doesn't offer a good solution here, because with a cancellation, it also comes the problem of defining uninterruptible regions. If a process can be interrupted, you will probably sooner or later want to define some cleanup logic. So releasing a database connection or cleaning up some resources, right? And this cleanup logic probably shouldn't be ever interrupted, right? So you need to define an uninterruptible region. And while you can interrupt virtual threads using thread interrupt, you cannot define these uninterruptible regions having only try-catch finally at your disposal. And IOs, since they are externally coordinated, offer a solution here. IOs also have a very nice property which allows you to separate the definition of a process from its sequencing, right? So you first describe the process. It's only a description, it's a lazily evaluated chunk of code. So once you create it, it doesn't run until it's sequenced with other processes. So you have to be very explicit as to how your concurrent program looks like, as to which process runs concurrently with other processes. Actually, when using features, it's quite easy to do some accidental concurrency, right? Because once we create features, the computations start running in the background. So here we have to be but with IOs, that's not true. Once we create IOs, it's only a lazy chunk of code, right? And only once we explicitly state that this process should run concurrently with this process, they will actually do once this is run in the end. So we can also get referential transparency and equational reasoning, which are nice properties when you try to understand how your code base works. And we also get very nice composability properties. So imagine having to define a process which retries a computation that has a timeout. Or maybe we want to describe a computation which has a timeout, but inside we do some retries, right? So these are two combinators used in a different order. So once retry is first, once timeout is first, and in another scenario, timeout comes before retry. So these are, of course, different computations, and these are very important details into how you describe your computations. But using IOs, but these IO libraries give us actually the tools to describe these things in a very composable and nice way, something that isn't available in pure Loom and has to be built on top of it. So yeah, summing up, where Loom shines is writing down sequential logic. So that's probably the majority of our, let's say, business code. Where asynchrony is really a technical detail, which is nice because it's faster and so on, but it doesn't do any good for the readability of the code to actually introduce asynchrony in that code. And here we represent our processes as code. Now, where IOs or futures shine is orchestration of concurrently running processes, right? So this is probably more niche code, but it's business critical. It's quite hard to get right. Here, asynchrony is a first-class citizen, and we might actually want to take advantage of this asynchrony directly in the code. And as before, readability is paramount, but it means a different thing over here, right? Here, by readability, we mean that we can see how these processes are orchestrated, how these processes interact with each other, communicate, and so on. And here, very often, it's very useful to have our process represented as a value. And we've just scratched the surface of various topics that are impacted by Loom. There's structured concurrency, there are thread locals, there's reactive programming, streaming, actors. All of these topics will in some way be impacted by Loom, and we probably even can't imagine right now exactly how, because once people get the tool ready, they will actually probably start developing some really cool stuff with it, as always happens. But I guess my important point here is that Loom solves some of the problems with readability with sequential code, but it doesn't really eliminate the need of the declarative concurrency. Quite the opposite. I think it will be easier and more programmer friendly to write down processes using either the code or the value point of views, using Loom or not. So a couple of reading points. So I will post a link later with the presentation, so you can take a look. There are two blog posts by the Loom team, which I think are very good introduction to the subject. Also a couple of blogs which I've written trying to understand how Loom might fit into the current world. Structured concurrency is a very interesting subject. I recommend reading these blogs as well as a couple of Twitter threads, which, despite the very concise, let's say, nature of Twitter, still often have very useful information. So that's all I had. So thank you very much for listening. I hope this was valuable, at least in some part. And as I understand correctly, we will now move to the spatial chat for Q&A. So